Hello students, welcome to the video lectures of speech and natural language processing. So today we will talk about stochastic and transformation based tagging in natural language processing. So what is the stochastic based and what is transformation based tagging? We will just see each one in detail. So under stochastic based, we have a couple of things to discuss, and under transformation based, we have a couple of things to discuss. So just we will start these two things. So let me introduce you this both tagging concepts first. So stochastic and transformation based tagging are two primary methods for parts of speech tagging, which is essential in many NLP tasks, such as syntactic parsing, machine translation, and named entity recognition. So when I say this named entity recognition, you already know it is to recognize the entities, whether that is a location or it's a, defining some person, or whether it is giving you some time, right? And these are all entities. So first one is stochastic tagging, which relies on probabilistic models, learning from annotated data. Okay. Annotated data to predict the tags for each word in a sequence. Second is transformation based tagging. This uses an initially tags the words, initial tagging process, so which is then refined iteratively by applying a series of transformation rules based on the linguistic insights. And then we'll first look into this stochastic based tagging. So stochastic tagging involves the use of probabilistic models to assign POS tags to words. These models use statistical information such as the likelihood of a word having a specific tag and the likelihood of a tag sequence occurring. So these three are the key stochastic tagging methods. First one is hidden Markov model. Next is maximum entropy model. Third one is conditional random fields. We'll see one by one. So first one is about hidden Markov model. So basically what happens in this hidden Markov model is it tries to assume the sequence of parts of speech tags, which as it forms a Markov process, meaning that the current tag will only depends on the previous tag. That's how its approach is. And it basically uses two kinds of probabilities. That is, one is emission probability, other is transition probability. So before we discuss, we just read the definition. A hidden Markov model is a statistical model used to describe sequences where each state in the model corresponds to a tag or label, and each state produces an observable output, that is words. So various components of hidden Markov model are: first is state called tags. These are hidden, such as parts of speech tags, and form the possible categories we aim to predict. Observation, that is words. These are visible and make up the sequence we are analyzing. Example is words in a sentence. Then we have transition probabilities and emission probabilities. So transition probabilities is this. You can see the probability of transitioning from one state to other state. That means it is saying that, so suppose let us say the probability of uh, let us say transitioning from one tag, that is di minus 1 a, to transforming to di. Understood? So this is the probability of transforming of one tag to the other tag. Then is emission probability. Emission probability states that the probability of observing a particular word given in a specific tag, which means, so the probability of word W will be given by tag T, right? That's how probability of WI or T. So how hidden Markov model works? So first one is it models the sequence. Second is inference with Viterbi algorithm. So what is modeling the sequence? So modeling the sequence is the given a sequence of observations. Observations means some sequence of words. Hidden Markov model attempts to find the most probable sequence of hidden states, that are tags. Inference with Viterbi algorithm. So the Viterbi algorithm is used to efficiently compute the best possible tag sequence, maximizing the joint probability of states and observations. So basically, what is this Viterbi algorithm is? It is a dynamic programming algorithm, we can say, which is used to find the most probable sequence of tags for any sentence. That is your Viterbi algorithm is. And the example for the hidden Markov model in POS tagging is given below. The cat sleeps is the sentence. So now it have got the tags here. So it has tagged the as determinant, cat as noun, and sleeps as verb. This is the tag given for each word which is there in the sentence. And the observation sequence is this: the cat sleeps. Okay, so determinant followed by a noun, then followed by a verb. This is what the sequence is. And then we have conditional random fields. So conditional random fields are a type of probabilistic model that combines the strengths of hidden Markov model as well as maximum entropy model. So like HMMs, they are used for sequence labeling tasks, but they avoid the independence assumptions of HMMs by defining a conditional probability distribution over sequence of labels. And this is the reason, why these conditional random fields are said to be more powerful than our hidden Markov models or maximum entropy models. So what does it do is it basically tries to capture the dependencies as it is mentioned over here. It tries to catch the dependencies that exist between the given words. Given words in the sense if there are some neighboring words which are incorporated as a broader range of features, there we try to tag them. Let me give you one example. When I say they capture the dependencies between the tags. So let's say John and uh, Mary. Okay. Let me, yeah. So John and Mary. So John and Mary went to the bank. Okay. So now you can see there are different kinds of words that exist in this sentence. So now what I told you is the conditional random fields are type of probabilistic model which combines the strengths of HMM and ENTs. So basically, this is said to be powerful since it tries to capture the dependencies between the tags and neighboring words. Okay. Now, what does it do is, so our conditional random field will take into account the relationship that exists between John, Mary, and bank. And thus, it will come to a conclusion that bank is referring to a financial institution and not any other else. That is what conditional random field will look. So these are the key concepts in CRFs. That is conditional random fields. First one is conditional probability of label sequence. Then is feature based. Then is graph structure. What are these? Let's see. So conditional probability of label sequence. So here I've directly modeled the probability of an entire label sequence given the observation sequence. So observation sequence is in the earlier I have seen the observation sequence. It seems to be as tokenized words from the given sentence in this slide. That's one. So observation sequence without making independent assumptions. Okay. Next is feature based. So similar to our maximum entropy. So conditional random fields uses a feature based approach, allowing for rich contextual dependencies. Then is about graph structure. So conditional random fields are typically represented as undirected graphical models where the labels are nodes in the graph connected by edges that represent the dependencies. So just consider this example, you will understand. So then we have maximum entropy. So maximum entropy models are a type of log linear model, we say, so which is used for classification of the tasks. So unlike these HMMs, maximum entropy models don't assume conditional independence and can take advantage of a wide range of features, which makes them more flexible for tasks like POS tagging or document classification. So basically, what does this maximum entropies do is they try to calculate the most probable parts of speech tagging. Okay, how does this do is they just try to consider all the possible tag assignments and tries to aim at some maximum entropy. That means it tries to make the least biased choice. Okay, that is we can say that it makes the least biased choice. Okay. So the key ideas in maximum entropy models. So first one is conditional probability. So maximum entropy models directly predict the probability of a tag given an observation without assuming any prior probability distribution. Feature engineering. Maximum entropy models use feature functions that capture various aspects of input data. These features may represent properties of individual words, surrounding context, and any other relevant information. Next is exponential form. So maximum entropy models define the conditional probability of a label y given an input x as, so let me write. For example, let me write an example here. For example, let us say there is a word called as bank. Okay. So now this maximum entropy model, so can consider the previous word and context to decide if it is a noun or verb. Okay, that's how yeah, the maximum entropy models work. So then transformation based tagging. So transformation based tagging is a rule based approach to POS tagging. So where the model learns a sequence of transformation rules to improve upon an initial tagging, starting from a simple baseline. Transformation based tagging iteratively applies transformation rules to correct tagging errors based on contextual clues, gradually refining accuracy of the tags. So key concepts of transformation-based tagging are initial tagging, transformation rules, iterative correction. So when I say initial tagging is nothing but it's a simple method which is used to assign an initial tag to each word. So suppose if you look at some kind of a lookup table, how does it exist? Similar to that, it have a lookup table kind of thing where each word will have some common tag for that. Okay. Like there could be some simple rules. If a word ending with some ing, likely to be it is likely said to be a verb. Such kind of rules. Then transformation rules, we call it as a rule learning. So a set of transformation rules is learned from this annotated data, and these rules are designed to correct errors by the initial table. Suppose changing of the tags from a noun to verb based on the previous word. If it is a model verb, we have to change it, right? In such a way. So then we have a iterative process or iterative correction. So where these transformation based rules will be applied here iteratively just to improve the tagging accuracy. Okay. So just if you consider a word like book, okay. So we understood this word book in our previous video lectures as well, where we considered to read a book and then to book a ticket. So how the word or the context or the meaning changes when we use this in different sentences. So now considering here, if the initial tagging assigns the word book as a noun in the sentence, they book flights, and a transformation rule would change it to a very easily to a verb, which because it like it is based on again the context. Okay, that's how iterative correction happens. So these are the examples. So suppose we have a sentence called the race was exciting. Initial tagging is each word is tagged based on its most frequent tag. So the as a determinant, race as a verb, was verb, exciting as adjective. So now transformation rule application after it is applied. So based on training data, the model might learn the rule change verb to noun if preceded by determinant. Since we have this rule, so applying this rule, we change the race from verb to noun. So which is resulting in the correct tag. Now the have become determinant. Race is noun now. Earlier you can see the race was verb and was is verb and exciting is an adjective. So iterative until convergence, the model continues to apply rules iteratively, improving the tagging accuracy with each application. So this is about transformation based time. Thank you, students.